So now we're going to learn about the different types of petroleum traps. So you can have an anticline trap, which is basically a fold trap, but it's an upfold trap, not a downfold trap. You can have a fault trap that could be a normal fault. It could be a reverse fault or a thrust fault, depending on the type of stress involved. It could be a salt dome trap, and it also could be a stratigraphic trap, noting that there are different subtypes of a stratigraphic trap. Now remember that the petroleum, the hydrocarbons, and the organic matter had to get mixed with sediment called kerogen, and then the kerogen had to go through don't call me, preferably don't and call, and then the petroleum had to come out of the source rock, go into a reservoir rock, and get trapped. So these are essentially the different ways that the petroleum could get trapped. And of course, once it's trapped, it got to be sealed off by a cap rock. So the first type of trap that we're actually going to is an anticline trap, and as you can see in this particular diagram, the sedimentary layers are folded up. In this particular case, and these are not symbols that you guys would really understand well, but this would have to be the source rock, so it's probably shale or limestone, and that's where the kerogen undergoes evolution into don't call, and as a result the petroleum gets released out of the source rock. So the petroleum comes up and it goes out into the sponge rock called the reservoir rock. Now that reservoir rock could be conglomerate, it could be sandstone, it also could be limestone or dolomite. And the petroleum, due to low density, tries to make its way up through the ground as best it can. However, because of the fold, the anticline fold, and also because of this layer right here, which is shale, in this particular case, this is acting as the cap rock, the petroleum cannot get out. So what happens is it builds up in this area right here. That's why you have the oil rig here, the petroleum rig here, that drills down into the anticline trap, and in this case strikes gas and oil. So the geology is perfect. We have an anticline trap, we have a source rock, we have a reservoir rock, and a cap rock. So everything looks awesome for petroleum in this case. The only reason why you probably wouldn't get petroleum in this particular case is that if there was never any organic matter that actually got buried down into the source rock. Otherwise, if you did have organic matter and you did get oil and gas, the obvious other reason would be if there was a break here in the anticline and the petroleum actually leaked out. That would be the only other choice. Here is a better picture of an anticline trap. So as it's looking here, the source rock is probably not evident in the diagram, so the source rock is probably down here. This would be the reservoir rock, all of this. So it's a nice spongy sandstone with good porosity and permeability. And this right here would be the cap rock, and as you can see, it's shale, so it's impermeable. Any petroleum that comes up goes up into the trap and can't get out. So we have gas right here, we have oil right here, and we have water right there. And here's your rig drilling down. So that's a really nice diagram of an anticline trap. Naturally, the rocks have to break, and so when they break, there's a hanging wall and a footwall. So you look at what the hanging wall is doing and relative to the footwall, and that's how you decide if it's a normal or a reverse fault. In this particular case, the hanging wall is going down and the footwall is going up. So this is a normal fault caused by tension, maybe at a divergent plate boundary. The reason why you need the faulting is so that the rocks no longer line up based on type. And so if you were to look in this place right here, you have sandstone, and it's right up against shale on both sides. So what happens is the source rock is down in the ground. That's where your organic matter is that gets buried, that undergoes don't and call. And then the petroleum goes up into the reservoir, which looks to be sandstone, and it can't get out on either side because this is a cap and this is a cap. So it builds up in this little area, and you get gas over the oil. And so this here would be a good place to drill. In this particular example, we have two places to drill because we actually have two completely different fault traps altogether. And that is common in areas where you actually get faulting, that you could actually produce from two different wells in two different fault traps. The other one is dome trap, and so basically the salt grows up mostly probably from an ancient ocean floor, a sea, and the salt is in a big dome. and basically the sedimentary layers kind of like basically get deposited on both sides of the salt. It's important to know that salt is like a caprock. It's impermeable just like shale. So if we were to look at, I see limestone right here, which could basically act as a source rock. Actually, underneath the limestone, there's actually shale that could also act as the source rock as well. Here I see a spongy sandstone, which is a reservoir rock. And here I see shale, which is a caprock. And so in here would be, so the oil, the petroleum, the gas, whatever, would come out of the limestone and the shale, go into the sponge. Can't get out because of the salt, can't get out because of the shale, so it actually builds up. In this particular case, the geology looks to be pretty good that you could have more than one salt dome trap. And so you could actually have one here, and you could have one here, one here, and one here. They could all be drilled from one rig, or you could probably drill 4 different rigs. It depends on the depth and that kind of thing, and how much is in each particular location, if they can do directional drilling or not. The other type of trap is a stratigraphic. This one we'll do is a limestone reef trap. And so limestone in this particular case is biochemical, so it's actually created by living things in a coral reef, and it is a really good reservoir rock. And as you can see over the top here, we have a caprock of shale that goes all the way over it. Shale is very impermeable, so stuff cannot get out. The source rock is probably not in the diagram, it's probably down here, so the petroleum tries to come up through the spongy limestone reef, and quickly realizes that it's buried by a layer of shale and it can't get out, so it builds up here in the reef. And so here's your drill rig that drills straight down into the trap. From the looks of it, there was another reef up here that basically grew later, and so there's actually 2 limestone reef traps in this one particular diagram. There's another type of stratigraphic trap called a on-conformity trap, and I will show you that one, particularly an angular on-conformity stratigraphic trap, in an upcoming video. I would like to mention that we always think of it as GOW, gas over oil, oil over water, due to density. So water got a higher density than oil, oil got a higher density than gas. And so once the petroleum hits the spongy reservoir and goes into the trap, it basically doesn't mix, it separates out based on density in the trap. And so that's always very important when you consider, when you're drilling, what you're going to hit first. All right, and so this is just different diagrams. And also, you don't need to get oil and gas. You could just get gas, you could just get oil, you could get both, you could get water, you may not get water, you could only get water. They're all different options depending on the organic matter that was buried. There's 2 ways that you can get petroleum out of the ground. You can drill it out, or you can mine it out. Now, most people don't think of mining when it comes to petroleum. They mostly think of drilling. I'm talking about surface mining, open pit mining, and the example that comes to mind for me in this particular case is the tar sands in Fort McMurray. So drilling can take place on land, like in Alberta, or on ice, like is happening up in the Arctic, or on water, like off the coast of Newfoundland in the Atlantic Ocean on our continental shelf. It's very important that you realize that petroleum really wants to get out. It's a very low density material, and it wants to get out, so it's under natural pressure. And that's why when you're drilling for this stuff, it's very important that drillers be cautious, because if you drill into a reservoir without knowing that you're going to hit it, the pressure could be high enough to basically the petroleum could force its way up through the borehole, blow out all the pipes, and actually tip over the drill rig, cause fires, major oil spills on the ocean floor. And so I'm sure everybody has seen footage in the news in the past about petroleum blowouts. I always like to think of a blowout like a can of Coke. And so if you were to shake up a can of Coke and someone was to open it because they didn't know you shook it, then pop goes everywhere. So there's a certain amount of gas in there that just obviously wants to come out on its own. In this particular case, there's probably 20% of the Coca-Cola that's going to come out on its own, no questions asked. And then there's probably 80% of the Coca-Cola that's obviously left, and you'd have to turn the can up on the side in order to get it out. The question is, you can't turn an oil reservoir up on its side to get it out. So, you know, what are things you do to get the petroleum out once the pressure is gone? You could pump in water to force it out. You could pump in gas to force it out. There's different things that you can actually do to get it out. Surface extraction has been taking place in Fort McMurray, and so basically the petroleum, and in this case it was crude oil, made it all the way to the surface and went into massive layers of sand, and some of the sand was lithified in the sandstone and some of it wasn't, and so we call this now, because of course because it was exposed to the atmosphere, a lot of the gases and volatiles escaped, making it really, really thick. So it's basically a really, really thick oil in amongst sand, and so we call that now the tar sands. So they've been basically open pit mining this for quite a while. There's a couple companies that come to mind when I think of the tar sands. I think of Syncrude and Suncor, and basically the petroleum is really thick. So what do? They typically take the petroleum and they do what's called steam injection, and basically the steam makes the petroleum, the hydrocarbons, I guess, less viscous and more runny, and so they're able to separate the petroleum from the sand due to steam injection. So that's one of the things you need to keep in mind when you think about the tar sands in Fort McMurray. Here's some pictures of it. I like this picture up here in the top right. Kind of just shows you how thick the sand is and how soaked and saturated it is with really thick petroleum. These dump trucks and excavators are massive, and I mean massive, and these open pit mines are massive. And it's just barely underneath some light vegetation in the ground in that particular area. When the petroleum comes out of the ground, naturally it needs to be refined, and the three different types of refining that takes place is distillation, cracking, and reforming. For distillation, the petroleum is basically desalted and dewatered first, and then they put it inside a distillation chamber. You have a lot of different types of hydrocarbons that are all mixed together, so the first thing you need to do is to separate those. It's also important that you realize that these different hydrocarbons are at different lengths, and basically to separate those different lengths of hydrocarbons is going to require different boiling points. So they can all be separated by distillation and heating, and typically that is highly linked to what we call cracking. So cracking is when heat is added to the chamber, and basically the petroleum separates into different fractions based on boiling points. And when I say different fractions, I mean chains of hydrocarbons with different numbers of carbons. So we talked about how up here this would be the lowest boiling point, down here you would have the highest boiling point, up here you'd have the lowest number of carbons, down here you would have the highest number of carbons. So here you get your oil, paraffin, wax, your oils, stuff to make asphalt, your jet fuel, your diesel fuel, your kerosene, your gasoline for cars like octane, and up here gases like butane and methane and ethane and stuff like that, and propane. So that's a fractional distillation chamber. For cracking, watch for heat, watch for fractional distillation chamber, and watch for separating based on boiling point. The third type is reforming, and so reforming is when you take smaller chains of hydrocarbons and you reform them into longer chains. So this is a human process, and basically it involves heat, pressure, and the use of catalysts, which are basically chemical substances that are used to increase the rate of a chemical reaction and make it go faster. So basically reforming, look for the word catalyst if it's on the public exam or a test, and also this is a human-made one. So now we're at a point in the course where we need to talk about sustainability and what it means, and I'll keep this relatively brief, but we are using petroleum at a very fast rate, and so if you were to look at it in terms of sustainability, we've had issues with the fishery, with the forest, and things like that in the past, so we need to ensure that we can actually maintain petroleum for many, many years to come. So we need to consider things that we can do as a society so that we can continue to use petroleum, but at a rate that we will ensure to have it for many generations to come.